Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Central University of Haryana. Today we are going to discuss about a module, the Clebsch-Gordon coefficients under the paper Quantum Mechanics 1. So the main points that we are going to be covering in this module are: first, derivation of the orthonormal properties of the Clebsch-Gordon coefficients. Second, to learn some useful symmetry relations between the Clebsch-Gordon coefficients. Third, to derive the expression for the Clebsch-Gordon coefficients with the help of recurrence relations. And finally, to learn a few examples to evaluate the Clebsch-Gordon coefficients. So, having introduced the Clebsch-Gordon coefficients, the triangular relations between the total angular momentum J1, J2 and J and the M-sum rule in the preceding module, we proceed to study here the orthonormal properties and certain symmetry relations between the Clebsch-Gordon coefficients. We shall also indicate briefly a method based on deriving a recurrence relation in the projection quantum numbers for fixed values of J1, J2 and J, where J1, J2 and J are the total angular momentum values for state 1, or rather for particle 1, particle 2 and the combined system, and apply it to show how this relation can be used to determine the expressions for the Clebsch-Gordon coefficients in a few cases. We present a couple of tables for some typical cases. Orthogonality relation of the Clebsch-Gordon coefficients. Now let us look at the orthogonality relations of the Clebsch-Gordon coefficients. So we start by writing the relation of the coupled representation with the uncoupled representation in terms of the Clebsch-Gordon coefficients. So the state vector Jm is equal to summation over m1, m2, bra vector j1, j2, m1, m2, ket vector jm, ket vector j1, m1, ket vector j2, m minus m1, where the bra vector j1, j2, m1, m2, ket vector jm are the Clebsch-Gordon coefficients, and we have used the relation m minus m1 for m2, and this gives us the result summation over m1 bra vector j1, j2, m1, m minus m1, ket vector jm, ket vector j1, m1, ket vector j2, m minus m1. So as discussed above, the bra vector j1, j2, m1, m minus m1, ket vector jm are the Clebsch-Gordon coefficients, where instead of m2 we have used the relation m2 is equal to m minus m1 also, and this we could do because m1 and m2 are not independent. Therefore we could denote the value of m2 in terms of m and m1, where m2 is simply m minus m1. Now, since the Clebsch-Gordon coefficients are elements of unitary transformation, therefore they must satisfy the orthonormal properties, orthogonality condition for Clebsch-Gordon coefficients. Now, thus using the above description, we have the state bra vector Jm, ket vector J prime M prime is equal to Kronecker delta J J prime, Kronecker delta M M prime, and this is equal to summation over M1 M1 prime bra vector J1 J2 M1 M minus M1 ket vector Jm bra vector J1 J2 M1 prime M prime minus M1 prime ket vector J prime M prime whole times bra vector J1 M1 ket vector J1 M1 prime times bra vector J2 M minus M1 ket vector J2 M prime minus M1 prime. Here again we have defined the Clebsch-Gordon coefficients as bra vector J1 J2 M1 M minus M1 Jm for the angular momentum operators or vectors J1, J2, M1 and M2, where M2 is defined as M minus M1, and for J1, J2, M1 prime and M2 prime, where M2 prime is defined as M prime minus M1 prime. Now, since the eigenstates are orthonormal, that is bra vector J1 M1 ket vector J1 M1 prime bra vector J2 M minus M1 ket vector J2 M prime minus M1 prime is given by the relation delta of M1 M1 prime times delta of M M prime. We get the relation summation over M1 bra vector J1 J2 M1 M1 minus summation over M1 bra vector J1 J2 M1 M minus M1 ket vector Jm bra vector J2 M2 bra vector J1 J2 M1 M minus M1 ket vector J prime M is equal to delta J J prime. So this relation gives the orthonormality condition, and in a similar manner we can also obtain the orthonormality condition or the relation in the inverse, that is the inverse orthonormality relation or condition, and that is given by the relation ket vector J1 M1 ket vector J2 M minus M1 is equal to summation over J bra vector J1 J2 M1 M minus M1 ket vector Jm ket vector Jm, where the bra vector J1 J2 M1 M minus M1 ket vector Jm are the Clebsch-Gordon coefficients. Now, multiplying both sides of the above equation by the Clebsch-Gordon coefficients J1, J2, M1, M minus M1, ket vector J prime M, and then summing over M1, we can rewrite the above equation as summation over J, ket vector Jm, bracket open, summation over M1, bra vector J1, J2, M1, M minus M1, ket vector J prime M, bra vector J1, J2, M1, M minus M1, ket vector Jm, bracket closed, and this turns out to be equal to summation over M1, bra vector J1, J2, M1, M minus M1, ket vector J prime M, ket vector J1, M1, ket vector J2, M minus M1. Symmetry relations. Now, if we look at the quantity that is there within the parenthesis or the bracket on the left hand side, we realize that it is simply the delta operator delta J J prime, and thus the equation reduces to the defining equation for the Clebsch-Gordon coefficients. So this can be written as summation over j ket vector jm delta j prime is equal to summation over m1 bra vector j1 j2 m1 m minus m1 ket vector j prime m ket vector j1 m1 ket vector j2 m minus m1, and this finally gives the result. The state vector or ket vector j prime m is equal to summation over m1 bra vector j1 j2 m1 m minus m1 ket vector j prime m ket vector j1 m1 ket vector j2 m minus m1. Similarly, another orthogonality condition on the rows and columns of a unitary matrix can also be obtained in the above manner, and the final result turns out to be summation over j bra vector j1 j2 m1 m minus m1 ket vector jm bra vector j1 j2 m1 prime m prime minus m1 prime ket vector j m prime is equal to delta m1 m1 prime delta m m prime, where the quantities within the summation over j are the Clebsch-Gordon coefficients for j1 j2 m1 m2, which is equal to m minus m1, and j1 j2 m1 prime m2 prime, where m2 prime is equal to m prime minus m1 prime. So among the three number pairs, that is j1 m1 j2 m2 and jm, where m is given as equal to m1 plus m2, we observe that there is a certain symmetry relations as a result of the triangular relations between j1, j2 and j, and the m sum rules that we have applied over here, that is m is equal to m1 plus m2. Symmetry relations. So using these above number pairs, that is j1 m1 as one pair, j2 m2 as the other pair, and jm, where m is equal to m1 plus m2 as the third pair, we can have some simple relations which exist between the Clebsch-Gordon coefficients when the roles of the angular momenta are interchanged, and which can prove to be very useful in the evaluation of the Clebsch-Gordon coefficients from those that are already determined. So we may write down these symmetry relations as the Clebsch-Gordon coefficient bra vector j1 j2 m1 m2 ket vector jm is equal to minus 1 to the power j1 plus j2 minus j whole times bra vector j2 j1 m2 m1 ket vector jm. This can also be written as in the form of another Clebsch-Gordon coefficient as minus 1 to the power j1 plus j2 minus j whole times bra vector j1 j2 minus m1 minus m2 ket vector j minus m. In terms of a third Clebsch-Gordon coefficient, we can write this as equal to j bra vector j2 j1 minus m2 minus m1 ket vector j minus m. Similarly, the Clebsch-Gordon coefficient bra vector j1 j2 m1 m2 ket vector jm can then be written as equal to minus 1 whole times j1 minus m1 whole times under root of 2j plus 1 upon 2j2 plus 1 whole times bra vector j1 j m1 minus m ket vector J2 minus M2, and the Clash-Gordon coefficient J1, J2, M1, M2, ket vector Jm can also be written as minus 1 times J2 plus M2 whole times under the root 2j plus 1 upon 2j1 plus 1 whole times bra vector j, j2 minus m, m2, ket vector j1 minus m1. Determination of the Clash-Gordon coefficients. So it is important to note over here that the three symbols introduced by Wegener and used in many textbooks is related to the notation used here as the brackets J1, J2, J3, M1, M2, M3 is equal to, or rather the matrix representation J1, J2, J3, M1, M2, M3 is equal to 1 upon under root twice J3 plus 1 whole times minus 1 to the power J1 minus J2 minus M3 bra vector J1, J2, M1, M2, ket vector J3 minus M3. Now, to determine the Clash-Gordon coefficients, we shall outline briefly the procedure for evaluating the Clash-Gordon coefficients. The simplified derivation is based on a recurrence formula for the coefficients. The first step is to apply both sides of the starting equation for the Clash-Gordon coefficients on the formula that is given by operator j square is equal to operator j1 square plus operator j2 square plus twice operator j1 dot operator j2, that is twice the scalar product of operator j1 and operator j2, and this turns out to be equal to operator j1 square plus operator j2 square plus lowering plus raising operator j1 plus dot lowering operator j2 minus plus lowering operator j1 minus raising operator j2 plus twice of j1z j2z. Here j1 plus is the raising operator for particle 1 and operator j1 minus is the lowering operator for particle 1, while operator j2 plus is the raising operator for particle 2 and operator j2 minus is the lowering operator for particle 2, and operator j1z is the z component of the total angular momentum operator for particle 1, while operator j2z is the z component of the total angular momentum operator associated with particle 2. Determining the Clash-Gordon coefficients. Now, if we recall from our previous study that while the state vectors Jm are the eigenstates of the operators j square and jz, that is the square of the total angular momentum operator and the z component of the total angular momentum operator, then the states j1 m1 and the states j2 m2, which can also be written as j2 m minus m1, are respectively the eigenstates of the operators j1 square, operator j1z, where operator j1 square is the square of the total angular momentum operator j1 of particle 1, and j1z operator is the z component of the total angular momentum operator j, and the operator j2 square and the operator j2z, where again These are the operators for particle 2. We use the relations given in the preceding discussion and also our knowledge of the raising and the lowering operators. That is, for particle 1, we can define the raising operator as operator J1 plus and the lowering operator as J1 minus. And similarly, for particle 2, we can define the raising operator as J2 plus and the lowering operator as J2 minus, and employ the relations given in the earlier discussion. Then, after doing some mathematical jugglery and manipulations, we can finally obtain the result, bracket open, j times within brackets j plus 1 minus j1 times within brackets j1 plus 1 minus j2 times within brackets j2 plus 1 minus twice m1 times within bracket m minus m1 bracket close whole times bra vector j1 j2 m1 m minus m1 ket vector jm, and this turns out to be equal to bracket open within brackets j1 minus m1 plus 1 times within brackets j1 plus m1 times within brackets j2 plus m minus m1 plus 1 within brackets j2 minus m plus m1 whole bracket closed whole to the power half whole times bra vector j1 j2 m1 minus 1 m minus m1 plus 1 ket vector jm, this whole plus bracket open within brackets j1 plus m1 plus 1 times within brackets j1 minus m1 times within brackets j2 minus m plus m1 plus 1 times within brackets j2 plus m minus m1 whole bracket close whole to the power half times bra vector j1 j2 m1 plus 1 m minus m1 minus 1 ket vector jm. Evaluating Clebsch-Gordon coefficients. So now in the above relations, the Clebsch-Gordon coefficients were given by bra vector j1 j2 m1 m minus m1 ket vector jm, and in the other equations it was given by bra vector j1 j2 m1 minus 1 m minus m1 plus 1 ket vector jm, and in the third line it was given by bra vector j1 j2 m1 plus 1 m minus m1 minus 1 ket vector jm. So the above equation basically gives the recurrence relation for the Clebsch-Gordon coefficients for the fixed values of j1, j2, j and m in the projection quantum numbers. So here what one needs to note is that while the Clebsch-Gordon coefficient on the left hand side has in its argument the quantum number m1, the term on the right hand side has the argument m1 minus 1 in the first term, and the argument in the second term on the right hand side is m1 plus 1. So in order to see how this recurrence relation is employed to get the expressions for the Clebsch-Gordon coefficients, let us now consider some specific case in which j1 is coupled to j2 equal to 1 to get the value of the total angular momentum j is equal to j1 plus 1, where we are taking 1 because j2 is equal to 1. So j is equal to j1 plus j2 is equal to j1 plus 1. Now let us call for brevity bra vector j1 1 m minus mu ket vector j1 plus 1 m is equivalent to x subscript mu. Example to determine Clebsch-Gordon coefficients. Now, as defined above, that is, x mu can be defined as bra vector j1 1 m minus mu ket vector j1 plus 1 m, where mu is m minus m1 is actually the value that we've been taking as m2 till now, which can take the values plus 1, 0 and minus 1. Since we've taken the value of j2 to be 1, so m2 can take values from plus 1 to minus 1 including 0, and substituting the values of j2 equal to 1, j equal to j1 plus 1, we get three recurrence relations for mu equal to 1, 0, minus 1. Example. Now, if we use the orthogonality relation for the Clebsch-Gordon coefficients, which for the present case can be written as x1 square plus x0 square plus x minus 1 square is equal to 1, where the subscripts 1, 0 and minus 1 are the different values of m2 or mu, then using this relation we have 1 upon x0 square is equal to 1 plus j1 plus m upon twice j1 minus m plus 1 whole plus j1 minus m upon twice j1 plus m plus 1, and this gives x0 square as j1 minus m plus 1 whole times within brackets j1 plus m plus 1 upon within brackets j1 plus 1 times within brackets 2j1 plus 1. So from this relation, since we see that this only determines the square over all phases, what we find is that the phase still remains to be determined, because this is here these relations are only giving us the square values, and this can be fixed by adopting the convention bra vector j1 j2 j1 j2 ket vector j1 plus j2 j1 plus j2 is equal to 1. So adopting this convention from this relation, what we have is that we are allowed to take positive square root, and since x1 is equal to 1, for m is equal to j1 plus 1, we may only take the positive square root. We can thus determine the first three Clebsch-Gordon coefficients. So, using the above method, the first three Clebsch-Gordon coefficients that are determined are given as follows. X subscript 1 is equivalent to the Clebsch-Gordon coefficient given by bra vector j1 1 m minus 1 1 ket vector j1 plus 1 m, and this is equal to under the root within brackets j1 plus m times within brackets j1 plus m plus 1 upon within bracket 2j1 plus 1 times 2j1 plus 2. Similarly, the second relation or the coefficient is given by x0, which is equivalent to the Clebsch-Gordon coefficient bra vector j1 1 m 0 ket vector j1 plus 1 m, and this is equal to under the root within brackets j1 minus m plus 1 times within brackets j1 plus m plus 1 upon within brackets 2j1 plus 1 times within brackets j1 plus 1. And similarly, the third of the Clebsch-Gordon coefficients, that is x minus 1, given by the bra vector j1, 1, m plus 1, minus 1, ket vector j1 plus 1, m. And this is equal to under the root within brackets j1 minus m times j1 minus m plus 1 upon within brackets 2j1 plus 1 times within brackets 2j1 plus 2. So the way we have determined these three Clebsch-Gordon coefficients corresponding to m2 is equal to 1, 0 and minus 1 respectively, or mu is equal to 1, 0 and minus 1 respectively, we can adopt a similar procedure to determine the coefficients for the case j1, j is equal to j1 when mu or m2 is equal to plus minus 1 or 0, and j is equal to j1 minus 1 when mu is equal to plus minus 1 or 0, that is m2 is equal to plus minus 1 or 0. It is important to note here that in the coupling of angular momentum j1 with the angular momentum j2 equal to 1, the total angular momentum j can have values that range from j1 plus 1 to j1 and j1 minus 1. And for each value of j, mu or m2 has the values plus 1, 0 and minus 1. So as a result, we can have, or rather we will have to write 9 elements in the matrix form. Sign convention. In obtaining the second and third rows, ambiguity in the overall sign of each row is once more found. We here adopt the convention in an ad hoc manner by specifying that Clebsch-Gordon coefficients for m2 equal to minus j2 shall be non-negative. This explains why in the third row the first element is to be taken as positive, and as a result the second has a negative sign. In the text, we have also discussed another example of coupling between J1 state, that is the total angular momentum J1, and the J2 state, that is total angular momentum J2 equal to half, which results in finding out 4 elements expressed in a 2 cross true matrix form. And for further details, the students can refer to the text. Now, let us summarize what all we have learned in this module. So, first of all, we learned how to derive the orthonormal properties of the Clebsch-Gordon coefficients. After that, we learned about some of the useful symmetry relations between the Clebsch-Gordon coefficients. And using these symmetry relations, we then derived the expressions for the Clebsch-Gordon coefficients with the help of the recurrence relations. And finally, we learned a few examples on how to evaluate the Clebsch-Gordon coefficients. And with this, we can actually, using all this knowledge, be able to evaluate the Clebsch-Gordon coefficients. Thank you.